Hello everyone, today in this video we are going to talk about the magnetic dipole moment of a current loop. So after this video you should be able to define magnetic dipole moment and derive the formula for magnetic dipole moment. We already know when a current flows through a conductor it produces magnetic field like this. So there will be magnetic field in each point of a conductor like this. This is another picture. You can see the magnetic field lines are out here, out here, out here. So the direction of magnetic field lines is given by right hand thumb rule. And let us take a conductor in which current is flowing in upward direction. And we already know the magnetic field lines are concentric circle around the conductor. So I'll draw a circle in such a way that half portion of the circle is above the conductor and half portion is below the conductor, and the portion which is below the conductor is represented by dotted lines. So now I'll use the right hand thumb rule. So if you grab a pencil in which the sharpened part is showing the direction of current, then the curling of the hand will show the direction of the magnetic field, and from this side it is going above the conductor. So I'll just put the arrow. So from the front side it is going towards the right. So this is the direction of magnetic field. So now let's consider a current loop in which current is flowing. So this is a plane perpendicular to the plane of the loop. So we already know the magnetic field lines are concentric circles. So I'll draw the circles like this at this point and at this point. So now I have to find the direction. So I'll use the right hand thumb rule. So out here magnetic field lines are going towards the right from this side. So I'll put the arrows. Now I'll also use the right hand thumb rule this side. So now you can see it is going towards the left from above the conductor. So I'll just put the arrows like this. So now you can see all the magnetic field lines are entering from this side and coming out of the loop from this side. So this is another picture. As you can see, if you use right hand thumb rule everywhere, so all the magnetic field lines will go upward. So it is entering from below and coming out from up. So this is another picture, one more picture. And not only from two sides, there will be magnetic field in each point of the conductor. So it will look like this. This is another picture, the magnetic field in 2 points only. Then here you can see magnetic field from each point. So you can see magnetic field lines are entering from this side and coming out of this side of the loop. Conclusion is a moving charge or current produces magnetic field, and a current carrying loop act as a magnetic dipole. Magnetic dipole means two poles of a magnet, north and south. So it act as a small bar magnet having one north and one south. Now we'll prove that the current loop act as a magnetic dipole. In the picture we have already seen there are two poles for a current carrying loop. So out here we'll prove mathematically. So magnetic field at the axial line of current loop is given by Q. So this we have already done in our previous classes. So this is how we derive the magnetic field line at the axial line. Now I'll multiply and divide by 2 pi, and I'll make the constant mu naught by 4 pi with one of the 2 pi, and I'll multiply 1 2 pi out here. So now you can see pi a square. A is the radius of the loop, so this is the area of the loop. So I'll write B is equal to mu naught 2ia by r cube. Similarly, the electric field at the axial line of electric dipole is given by this. E is equal to 4 pi by epsilon naught into 2p by r cube, where p is the dipole moment of the dipole. So this is how we have derived this. Now we'll compare this two equation. So this is magnetic field, this is electric field, they are equivalent. This is one constant in magnetic field and this is the constant in electric field, and this 2 by r cube and this 2 by r cube are similar. So we are left with this ia and p. So they should be similar because the formula are similar. So now this ia is equivalent to the dipole moment in the magnetism. So I can write Ia is equal to m, which is magnetic dipole moment. So this product of current and the area of the loop is similar to that of dipole moment in the magnet. If you have n turns in the loop, then you have to multiply it with n to get the magnetic dipole moment. So unit of dipole moment is ampere and for area is meter square. Magnetic dipole moment is a vector quantity and its direction is perpendicular to the plane of the loop, and it is given by right hand thumb rule. So now you can see this dipole moment is perpendicular to the plane of the loop, and if you curl your finger in such a way that the curling of finger shows the direction of current, then thumb shows the direction of magnetic dipole moment of the loop. Out here also, if the current is going towards the left, then magnetic dipole moment will be opposite. So this is the same notes, you can pause and copy. Okay, now let's find the magnetic dipole moment of an atom. So this is a picture of atom. The radius is r and electron is revolving around. So electron revolving around means charge is flowing, and flowing charges produces current, and current carrying conductor or flowing charges produces magnetic field. So because of this we get magnetic dipole moment in the atom. So we'll consider an atom and let r be the radius of circular path and let v be the velocity of electron. As electron is going towards the right from this side, so current will be in opposite direction, and using right hand thumb rule, magnetic dipole moment will be in downward direction, and L is the angular momentum of the electron in its orbit. Angular momentum means momentum into this radius, mvr. So now let's derive the magnetic dipole moment of an atom. So I'm considering the same case out here. So these are the things which we have already discussed, and t is the time period for the revolution, and to complete one revolution around the nucleus it takes time. So we know speed is equal to distance by time, so v is equal to 2 pi r by t and t is equal to 2 pi r by v. So this is the time required by the electron to complete one revolution. So we know current is charge by time, so charge is charge of electron and time is the time taken for one revolution. So I'll put the value of t 2 pi r by v, so this will become I is equal to ev by 2 pi r. Now the magnetic dipole moment m is given by current into area, so current is ev by 2 pi r and area is pi r square, area of the circle. Now this pi and pi get cancelled, so and r with r square you are left with evr by 2. This is the expression for magnetic dipole moment of the electron, but the problem out here is velocity. We don't know the velocity of electron, so we have to find the velocity of electron. So in order to do that, I'll make use of angular momentum of the electron. Angular momentum means linear momentum into the radius of circular path. So mv is the momentum of electron and r is the radius of the circular path. So for mass of the electron I am using me so that I don't get confused with the magnetic dipole moment m. According to Bohr's quantization condition, the angular momentum is integral multiple of h by 2 pi. So h is the Planck constant. So according to Bohr you can write angular momentum into n, which is integer, h by 2 pi. So I'll compare these two equations now, 2 and 3. So I'll get MEVR is equal to NH by 2 pi. So velocity is nh by 2 pi r me. So I got the value for v, so I'll put it in the equation, that is equation number 1. So this is the equation number 1. So if you put the value, this term will come into the denominator. So this is ENHR divided by 4 pi r me. So r get cancelled, so you are left with m is equal to n eh by 4 pi me. Now if you see these terms inside the bracket, they all are constant. E is constant, h is constant, 4 pi is constant, and mass of the electron is constant. We already know the values. So if I put the value, I'll get 9.27 into 10 to the power minus 14. So out here I am writing mn, which indicate the magnetic dipole moment of electron in nth orbital. So for first orbit I can write m1, for second orbit I can write m2. So the above expression gives the magnetic dipole moment of an electron in nth orbit. So if you put n is equal to 1 for the first orbit, so you have to multiply this term with 1. So you will get m1 is equal to 9.27 into 10 to the power minus 14 ampere meter square. So this is the magnetic dipole moment of the electron, which is revolving in orbit number 1 of the hydrogen atom, and this magnetic dipole moment we call it Bohr's magneton. Now you can try these questions, and it is saying a hydrogen atom has the radius of 5.1 angstrom. Angstrom means 10 to the power minus 10 meter, and velocity is given 2 into 10 to the power 6 meter per second. So you have to calculate the current, magnetic field, and the magnetic dipole moment. So for current you can use this formula. For magnetic field, due to a circular loop at its center is given by this, and magnetic dipole moment is given by this. And next question, this is also similar question. Out here radius is given and frequency is given. So from frequency you can find the time period, and you can find the magnetic dipole moment. Next question, 7 ampere is flowing through a circular coil of radius 1 centimeter, and this coil is kept in a magnetic field. So if a coil is kept in magnetic field, it rotates due to the force due to the magnetic field. So you have to find the maximum and minimum potential energy. So using this formula you can find magnetic dipole moment, and so potential energy, the formula for potential energy is minus mb cos theta. So this is B, magnetic field, and m you have found out. So for minimum potential energy theta is 0, for maximum potential energy theta is 180 degree. So you can put the values and get the answer. Okay, now we'll summarize the video. Current carrying loop act as a magnetic dipoles. So you can see it produces small north pole and south pole, so it is same as a magnetic dipole, and the direction of magnetic dipole can be found out using right hand thumb rule. The curling of finger shows the direction of current in the loop, and thumb shows the direction of magnetic dipole moment. And the formula for magnetic dipole in nth orbital is given by mn is equal to, so you can write mn is equal to n is equal to e h by 4 pi me, and if you put this value and n to be 1, then you will get the Bohr's magneton. Bohr's magneton is the magnetic dipole moment of the electron, which is revolving in the first orbit of hydrogen atom. I think this is the end of the video. Don't forget to give right hand thumb rule to my video. Thank you.